Assalamu alaikum everyone. So we're going to start with our new topic, which is Theodolite traversing. So before we begin our chat about Theodolite, first let's quickly review what is traversing. So traversing is when you set out a series of connecting lines uh, and whose ends have been marked. So basically what you do is you set out different points in the field and those points are joined together by connecting lines, and you can have two types of traverses. Either you can have a closed traverse or you can have a open traverse. And we have also discussed what is the difference between traversing and triangulation. So in traversing there are mainly two different measurements that you are interested in. One is the distance between consecutive points, and the other one is the measurement that ascertains direction of your projection. So you can get that direction in the form of angles, or you can get that in the form of azimuths or bearings. So if we talk about angles, so we studied how to plot interior angles using prismatic compass. But now we have a very basic, simple instrument that can replace the prismatic compass and that can directly give us interior angles, exterior angles, deflection angles. So whatever angles you want to measure in the horizontal plane and also angles that you want to measure in the vertical plane. So first let's talk about the horizontal angle measurement. So we can either measure interior angles of a traverse or exterior angles, and basically how you proceed with it is that once you have located the points, you place your instrument at any station point. So let's say I place it at station E. I center my instrument above the station point the same way we used to center prismatic compass. Then I, looking through the telescope of the instrument, I locate the station point A. So that would be a ranging rod or any leveling staff placed above that station point. And when I bisect that ranging rod or leveling staff, I set my instrument equal to 0, and then I rotate my instrument so that I bisect the other point, and then the angle that my instrument would give me would be the interior angle E or the angle AED. Now this is or the plotting of it or the measurement is similar to how you used to measure angles on a piece of paper using your protractor. So we used to place our D, the 0 point, exactly on the point from where we want to measure the angle, and one of the sides would be aligned with one side on the piece of paper, and then the other side would give you what the angle is between the 2 points. So this is similar to how a theodolite works in essence. Now, once you have these interior angles, there is a check that you can apply if it is a closed traverse, that the sum of interior angles should be equal to n minus 2 into 180, where n is the number of sides of the traverse, and the sum of the exterior angles should be equal to n plus 2 into 180. And the other sort of angles that we can lay out are deflection angles. So deflection angles are pretty much useful in open traverse case where you want to set out different connecting lines, like in our projects with roadways or railways, electric supply lines, so all of those things. So deflection angles are your deviation from your straight path. So let's say this is the path that I want to lay out in the field, and I start from over here. So up till some distance, my path is straight, but after that, there is a deviation from the original path. So this were the path had there been no deviation, and this angle, which measures the deviation from the original path, is called as deflection angle. And since my original path was straight and the deviation is towards the right of it, so there would be a rightwards deflection angle. Similarly, now this is my original path and next deviation is at this point. And if you want to lay out this deviation, you would place your theodolite over here, set this line at 0 degrees, and rotate your theodolite in this direction until you reach that specific angle, and then this path would become your original path or the new path. Now, in this case, the deviation was towards the left of the original path, so that's why you denote it like this, whereas previously it was denoted like this. So that tells you about the direction of the deviation or direction of the deflection angle. So they are really useful in setting out roadway projects or railway projects and similar projects. So then we have traversing by azimuths. Like we have discussed that azimuths give you direction from the north. So this way, it is easier for you to set out the direction of your traverse, something that we have studied in detail in compass traversing. And then comes the next path. So one step of the traversing was to set out the direction using the angles, and the second part is measuring the length of the sides. And to measure the length of the sides, again, we have studied a number of different ways we can do that. But there is a one more simpler way using the same instrument. So that really reduces the works. Theodolite can not only give you horizontal angles, it can also give you horizontal distances as well. And we'll see how we can do that in a little while. So this is introduction to theodolite traversing. So theodolites are basically instruments with which you can measure angles in the horizontal and the vertical plane, and you can do that with very high precision. So theodolites can be used for setting out horizontal angles, directions, measuring horizontal distances, measuring angles in the vertical plane, measuring heights of the objects, measuring deflection angles like we discussed, and with some addition of or upgradation of the instrument, we can also measure bearings, azimuths, and this instrument can also be used for ranging of lines since this instrument has a telescope. So when you have a telescope that has zoomed in vision and that also has crosshairs with the bullseye, you can basically use that telescope for all the purposes we used it before. So with some modifications, the theodolite can also be used as a leveling instrument as well. So now we'll discuss some types of theodolite. So first, the classification based upon telescope. So like we discussed previously in auto level, that telescope is the part of the instrument that helps you to get enlarged vision, and it has two ends. One at one end you have the objective lens, at the other end you have the eyepiece. So that is basically the telescope. Now we have two different types of theodolites based on the type of telescope that we have. We can either have a transit theodolite or we can have a non-transit theodolite. The difference is very simple. In a transit theodolite, the telescope can be revolved through a complete revolution about its horizontal axis in a vertical plane. Let me explain it with the help of a diagram. So these are examples of our transit theodolites. This one is available in the lab. So this is the telescope over here, object glass and the eyepiece at the other end. At the top, you have the sight finder. So similar to the auto level instrument, the sight finder is used to locate your objects because usually we are viewing objects which are very narrow. For example, a leveling rod or a ranging rod. And since the telescope gives you an enlarged view, it is difficult for you to locate your objects sometimes. So that is why you can use the sight finder to locate your object, and then once the direction of the instrument is set, then you can look through the telescope to read off the leveling staff or to just bisect a ranging rod. Now this telescope was fixed in the case of auto level, but fixed in the sense in the vertical plane. You could rotate the instrument in the horizontal plane, but in the vertical plane the telescope was fixed. But in this case, you can rotate the telescope about the horizontal axis in a vertical plane. So you can move it up and down. So you can view the objects which are above or below the height of the instrument. And if you can rotate this telescope to a 360 degrees, so then it's called as a transit line. And if you cannot rotate this telescope through 360 degrees, that means the theodolite has it's called a non-transit satellite because the telescope has some limitations of to the extent it can be revolved about the horizontal axis in a vertical plane. So this gives us a lot of benefits. We can measure angles of elevation, angles of depression, And so basically that is why this is very helpful. So these two are examples of transit theodolites, and this 6 second and 5 second represents the least count of the instrument. And over here we have non-transit theodolites. So as you can see, there is a limit to what you can revolve this telescope in the vertical plane. So earlier we could do a whole 360 degrees revolution, but in this case there's a limitation. So these were called as non-transit lights. So they are non-existent now, but this is the difference between transit and non-transit lights. Then we have classification based upon angle measurement. So there were, with time, there were a number of different ways by which the instruments measured angles. So earlier we had vernier scales inserted in the instrument. So when you used to rotate the instrument in the horizontal plane about the vertical axis, you could read off the vernier scale. Then you could read off a micrometer scale. But now we have electronic or digital theodolites. They have a screen, and when you rotate your instrument, the angle keeps on changing on this small screen, and you can read it off directly. So now let's see some different parts of the theodolite. Firstly, we have this telescope over here with the objective and the eyepiece at the other end, and you have some focusing screws to focus the image. Then we have a sight finder at the top of the telescope. Then we have optical plummet. So basically, when you look through the optical plummet, you get an image of the tram. So this little device inserted onto theodolite allows you to center your instrument above a station point, which is very important while measuring angles. So earlier, when in prismatic compass, we saw that we used to do the same thing using a plumb bob or dropping a stone. In this case, we have this optical plummet that gives you view of the ground, and that has a reference point so that you can know when the instrument is exactly above the station point. Then we have the circular bubble over here that helps you to level the instrument. Similarly, some instruments also have a plate bubble in addition. Then we have the base plate at the bottom. So this is placed on the tripod stand. And then we have three leveling screws, just like we used to have in auto level, so which are used to level the instrument. Then we have horizontal clamp or horizontal slow motion, and vertical clamp or vertical slow motion. So, like we discussed earlier in the case of auto level, when you look through your telescope, you get an enlarged view. And sometimes when you have to change your view just by a small amount, so let's say you are trying to bisect a ranging rod, but you need to move your instrument left or right just a little. But since you are looking at in large view, by moving it just a little, the image moves by a lot, and you miss the bisection. So that is why, in order to move it very slowly, left or right, you use the horizontal slow motion or this screw over here. And similarly, if you want to rotate your telescope in the vertical plane, you have this vertical clamp or vertical slow motion over here. So now let's see some terms. Centering. So centering is setting of your light exactly above a station point. So this is extremely important because if you're not centered above a station point, that means you won't be getting an interior angle. You would be getting some other angle. So it's very important to do this. And like we discussed, this is possible by using the optical plummet that allows you to do it in a very accurate way. Then the second term is called transiting. So transiting is when you rotate your telescope through 180 degrees. So that means if, as of now, the observer is standing over here looking through the eyepiece, and this would be the line of sight. Now, the transiting means you rotate your telescope through 180 degrees so that now the objective would be towards the other side, the eyepiece would be at this side, and the observer would have to move around the instrument to this side, and now the view or the sight would be into the paper in this direction. So when you rotate your telescope through 180 degrees, that is called as transiting. And what that results in, it results in the change of phase of your light. So we have phase left and phase right. So that means we have this part of the theodolite which is called as a vertical circle that is an inbuilt feature in the instrument that tells you that the instrument is uh, leveled in the vertical plane, or you could say that the vertical axis and horizontal axis are at 90 degrees. So that could be on either side of theodolite in different models. I usually we have a reference mark that tells you that this side is the side of the vertical circle, or the vertical circle is on this side, or it could be on the other side of the theodolite. So usually you usually have a circular built on one side, or you have a reference point. So let's say in our case the vertical circle is on this side. So when the observer is standing over here and looking in this direction, and the telescope objective is over here and eyepiece is on the other end, so when you are standing over here and looking in this direction, the vertical circle is at your right. So that means you are using the face right when the vertical circle of the light is on the right side of the observer. And when you transit your telescope, that means you rotate the telescope to 180 degrees. Now the objective gets on the other side, eyepiece is over here. The observer would move around and come in this position, and now the observer would be looking in the other direction. And now the vertical circle, the same vertical circle, is on his left side. So that means now we are in a face left position when the vertical circle of the theodolite is on the left side of the observer. So face left and face right basically help you in getting two set of readings, and the two set of readings can reduce the error, because in one case you rotate the instrument in one direction, in the other case you rotate the instrument in the other direction. So the error as a whole is minimized. So usually it is recommended that when you are reading out the same angle, you do it once using the face left and once with the face right, and that eliminates error, some sort of errors that could be present in the instrument. So the changing phase, like we discussed, bringing the vertical circle from one side of the observer to the other, and then we have the line of collimation. So, like we discussed in the case of water level, it is an imaginary line that passes through the intersection of crosshairs at the diaphragm. So that means when you look through the telescope, you get a circular vision, and in the center you have intersection of diaphragms, and at the center you have the bullseye. So the imaginary line that passes through that bullseye and optical center of the object glass and its continuation, that is the line of collimation. So that is basically your line of sight or your plane of sight, and that is called as line of collimation. Then we have axis of bubble tube. So it is a straight line tangential to the longitudinal curve of the plate level tube at the center. The axis of plate level is horizontal when the bubble is centered. So like we had in the case of auto level, we have the circular bubble, and that is used to bring the instrument to a level position, a horizontal position. And when it comes in the horizontal position, that means a tangent to that bubble is completely horizontal, and that is called as the axis of the bubble tube. So that basically helps you in leveling the instrument. So now again, some different parts that we studied before: horizontal slow motion, vertical slow motion, the telescope. Then we have the tripod at the bottom and the trivet or base plate. Above that, we have the foot screws. Then the digital display. On the display, you see some different buttons that have various functions. So on the function side, you can set your function as face left or face right, set the angle to zero, hold the value of the angle, and some different functions. And on the screen, the angle is displayed. So when you keep on rotating the instrument, the angle keeps on changing over here, and you can note down the reading. Similarly, you have a plate bubble over here and the circular bubble on the other side, and also an optical plummet to center the instrument, and the plate bubble and the circular bubble to level the instrument. And when I talk about the temporary adjustment of the theodolite, so the first thing that we have to do before setting out the instrument is to set the tripod stand above the station point and to open it up to a reasonable height. Then fix the instrument above the tripod and roughly level the instrument using the tripod stand. Once that's done, you look through the optical plummet and try to center the instrument above the station point. After that, you use the foot screws to precisely level the instrument. Now, once you do that, there could be a case that your centering gets out while when you look through the optical center. Then you open up the instrument and move the whole assembly above the tripod head just a little so that you achieve centering and leveling both at the same time. Once that's done, you use the focusing screws to focus your image so that there is no parallax, and then you're ready to take the reading or take the angle. So these are the steps explained in sequence. So setting up the tripod, setting up the instrument, leveling it, centering it, focusing, and then taking the reading. So now that we are ready to take the reading, uh, first let's talk about the horizontal angles. So there are two methods by which you can measure horizontal angles. One is called as a repetition method and the other one is called as reiteration method. So let's say we set up our instrument above the point B and we want to measure the angle ABC. Now there are two ways to do this. One is to locate either point A and set this line equal to 0, or locate the point C and set this line equal to 0. And then you rotate the instrument, locate the other point, and then we are ready to note down the reading. So in repetition method, what we do is that let's say this is the angle that we want to measure, angle AOB. We set up our instrument at the point O, we center it, we level it, then we locate the point A using a ranging rod, set this line equal to 0 degrees, rotate our instrument clockwise, locate the side B or the point B using a ranging rod, and note down the angle. Now we have the interior angle AOB, it's 30 degrees. But in order to minimize the error, we can use repetition method in which we take the same angle again and again. So that means you took the angle once, then you again sight the point A, set the angle equal to 0, take the angle again, and do this 3 or 4 times. And then you take the average, and that uh, minimizes the error in your final value. Or the other way is you take one angle, so that becomes 30, then you press hold, so that means now your angle won't change. Bring your instrument back to the point A, release the angle, and measure it again. So on the instrument, the angles would keep on adding up, and then you can just take the average. So this is called as repetition method, in which you take the measurement again and again, and then take the average to reduce the error. Alternatively, the other method is called as reiteration method. In reiteration method, let's see. So now you want to measure the angle AOB, and you also want to measure the angle BOC and COD. One way is you use repetition method once for this angle, once for this angle, and once for this angle. But that would take up a lot of time. Alternatively, what we can do is we can place our instrument at O, center it, level it, locate the station point A, set this line equal to 0 degrees. Rotate your instrument, locate the point B, and note down the reading. Then keep rotating the instrument, locate the point C, again note down the reading. Keep rotating the instrument, add B, again note down the angle value, and then complete the full circle and relocate or rebisect the point A. Now, initially you set the angle equal to 0 at the point A. When you complete the whole circle, your instrument now should give you 360 degrees. If it doesn't, it means that there was some error in the measurement. Now, this process is called as a reiteration method, in which you close up the horizon and you do a complete 360 degrees. This method is preferred when several angles are to be measured from a single station. So when you want to measure a number of angles from a single station, instead of doing the repetition method again and again for every angle, you can just use the reiteration method once, and that will give you multiple angles in a single go. But while using the reiteration method, a good practice is that first you measure the whole circle using a face left, and then you do the same process in the second set using the face right, and then take the mean of the two readings, one from the face left and one from the face right, so that minimizes the error even further. And this is where the face left and face right come in. It is usually recommended to take the readings using both the faces. So that really tells you about the condition of the instrument. If the instrument gives you the same readings from both the faces, that means the instrument is working fine. So the face left and face right are basically conventions that we use. So that was all about the horizontal angle measurement. Now let's talk about the vertical angles. So since our instrument has this capacity that the telescope can rotate in the vertical plane about a horizontal axis, so we can measure angles in the vertical plane by bisecting points which are above, at equal height, or below the instrument. So basically what we can do is we can measure two different sorts of angles, angle of elevation and angle of depression. So once you have set up your instrument at the station point and the telescope is completely horizontal, so that gives you, or you can set that angle as 0, and then you bisect any point above and note down the reading of the angle on the instrument. So that would be the angle of elevation. Similarly, below the horizontal position, you get the angle of depression. And if you want to get the total angle, you can add up the angle of depression and the angle of elevation. So one way is to do it with the zero line when the instrument is leveled and horizontal. The other way is to take the angle from zenith. So zenith is a word which is used for the highest point in survey. We use it for the point which is vertically above the observer, exactly above the observer. So the point which is in alignment with the vertical axis of the instrument, that is called as the zenith. And from there you can again measure any angle. And when you rotate the telescope through complete revolution, the complete revolution should come out to be 360 degrees again in the vertical plane. So you this can also act as a check in vertical angle measurement. So some errors in angle measurement, we can have systematic errors or unsystematic errors. Uh, the errors which remain constant through every reading, and errors that can keep on changing with every reading, so they can be random errors. And they are due to a number of different reasons. So one reason is non-adjustment of plate bubble. So that means even though your bubble tells you that your instrument is level, but in essence it is not. That means the axis is not exactly perpendicular to the vertical axis, and that can introduce error. Similarly, the line of collimation not perpendicular to the horizontal axis. So you can rotate your telescope in the vertical plane, but in the horizontal plane, the whole instrument moves as a whole. And the angle between the line of collimation or the line of sight and the horizontal axis of the instrument is 90 degrees. And if that is not 90 degrees, that means there will always be an error in whatever measurement that you take. Similarly, the vertical axis of the instrument is not perpendicular to the horizontal axis. So the two axes of the instrument, the horizontal axis and the vertical axis, are not perpendicular to each other. So that means there will be problem in leveling and taking angles as well. And then we have optical plummet error. So since we centered our theodolite using the optical plummet, so even if your optical plummet is telling you that the instrument is above the station point, you can make sure by hanging a plumb bob from the center as well. And if both the methods simultaneously tell you that your instrument is centered, that means your optical plummet is working fine. Otherwise, there could be an error in your optical plummet. Then we have different human errors. These are basically caused by your own mistakes, and they can be of numerous types: incorrect leveling, incorrect centering, incorrect bisection of the points, number of reasons. And then we have natural errors. So like we discussed in the case of order level as well, so strong winds can cause an error, there could be a refraction error, there could be settlement error. So all of these would be categorized as natural errors. So this is it for this slide. Now I would like to just sum up what we have discussed about theodolite. So when you set up a theodolite above a station point, you have to carry out centering, leveling, and focusing of the eyepiece so that you remove the parallax, and then we can take the angle. And this instrument allows you to calculate angles in the horizontal plane. So horizontal angles, vertical angles, horizontal distances and also vertical distances. And we will talk about how we can measure horizontal distances using Theodolite, and also how we can measure vertical distances as well. So this is it for this lecture. I'll see you in the next lecture on the same topic. Thank you.